Hello everybody, welcome to today's class seminar. We are always very proud of the speakers we are hosting, but we are even more proud when the speaker is one of our own. I am triple proud because I'm also his supervisor. Monroe graduated from the University of Maryland, Baltimore County, DC. Graduate fellowship, as well as the German fellowship, which is a PhD. He received also our master's in robotics. He was the leader of one of the 5 teams that became finalists in the KUKA competition and presented his work at the Monroe Fair in Germany last April, and quite a long CV actually for being a final year graduate student. And he received also the outstanding teaching assistant award of mechanical engineering. As Dan and several others can testify, he has been really always one of the top people in the outreach activities. And usually when we are judging about tenure, we are saying about research, teaching, and service. And as a matter of fact, Monroe is already all 3 of them actually now. And I am very eager to listen to how he will present today because he will be also the interview.
Thank you very much, Kostas. So today I'm going to talk to you about robotic assistants and specifically how you can have manipulators effectively be robotic assistants. So first I'm going to motivate assistive robotics. Why are they important? So you can think of jobs that you want to make more safe. If you want to handle dangerous chemicals, for instance, maybe you want to have a robot that can help you carry something in a dangerous situation, a disaster relief or a battlefield. Or maybe you actually would like a robot that can manipulate things to help you for convenience. So here you have someone who's paralyzed, the robot is helping them have a drink of water. You can imagine carrying things again, you can imagine the robot serving you some food, and again, maybe experiment preparation. So all of these scenarios motivate why you can imagine having these assistive robotics. So actually, this is actually a pretty old concept, but what they need to actually be able to do is they need to be able to perform complex tasks. They need to be able to adapt to disturbances and poorly modeled tasks, as well as operate with high performance in new and changing and dynamic environments. So this next video that I'm about to show you is actually made, was 2008, where they actually had a first robot from the University of Tokyo doing this.
Japan's top university, scientists are studying the future of household chores and their solution to mopping, laundry, and cleaning up the kitchen. Well, it lies in the hands of a robot known as AR, or Assistant Robot. AR has a host of high-tech functions which are possible because the robot can see 3-dimensional objects.
This is the first launch of a robot that will be able to help with household chores in an era of an aging population. We can show people we can do it.
This mechanical maid is capable of more than just serving breakfast in bed, and at 130 kilograms, it's no lightweight when it comes to polishing floors. But don't get excited just yet. The research center says it'll be another decade or 2 before the 1.5-meter robot can be mass-produced.
So this was a great presentation of motivating why you'd actually want to have these robots, helping an aging population. But as they hinted, it wasn't quite ready. And so I'll go to this next video.
Could you use a little extra help?
Right, and this is fast forwarding a little bit. So this was done in 2011, and the idea here was to have 2 robots that work together to actually make you a pancake. So for us, this is a very simple task, but you'll actually see how much time it actually takes this robot to do it. So in this operation, they actually plan the path for the robot to actually open the door. And as he discussed, he says, we actually use a little bit of tactile sensing actually to help place our hand as we get close. But majority of the task has been really well modeled. They actually know where the door is, and they use these beacons to help them solve this issue. And so here you can see the robot slowly open the fridge door after a few minutes, and this would be a lot faster for you or I to do. So here, I fast forward a little bit to them actually having one of the early KUKA arms do flipping of a pancake. They're so excited because we're able to do this seemingly simple task. And if you actually work in manipulation, you actually will realize that a lot of that was even open loop as they even began to do that. They localized the pancake, but after they had it, they took a lot of things for granted when they went to flip it. So this is a more recent application.
So at first, Tim was cooking his recipe, and his hand movements were recorded by our digital motion recording system.
And now the robot starts the melted butter with a spatula.
So what happens in this video is a chef actually mimics the motions that the robot arm needs to perform. But if you look very closely, these different containers are actually on little carefully placed coasters that keep them in place. And everything is filled to the right brim that it needs to perform this task. So if you actually wanted to have a robot chef, it needs to be able to handle a lot more dynamical situation and not simply just repeat the motions or joint feedback that's given to it. So we want to make these systems more complex, more autonomous. So how can we do that? So you can think of many of these tasks that you'd like to be able to complete. And what's really nice is if you solve some of these things, some of them will have overlap between different scenarios where you'd actually want to use it and be applicable to multiple end users. So we're specifically interested in the wet lab robotic assistant. So how can we actually help the pharmaceutical scientists? So we were approached by GlaxoSmithKline. They said, it would be great if you could have a robot that could be introduced into the lab and help us pick up some of the things that we're losing here in terms of time by having a robot that can assist us. So one was having a robot that could actually help prepare these experiments. Another case you can imagine is having a robot that could carry something in a cluttered environment. You can imagine replacing and restocking equipment, possibly experiment cleanup, as well as maintaining cultures while the scientists are away, for instance, on the weekend. So in my dissertation, I tried to focus on just these two aspects, and these will be the focus of our talk. So the precision pouring for experiment preparation, the main goals here are we want to be able to pour from containers that are already existing in the lab. You should just be able to roll up and use their containers. You need to be able to pour precisely. You need to be able to pour quickly. And then you don't want to have a lot of tool changes. You want to be able to just use the manipulator you have so that you can transition to another task when you're ready. So motivating this for the research lab scientists, we were told that when an R&D scientist prepares an experiment, they spend a lot of time simply pouring and mixing these buffers, and this actually adds up a lot to 12% of their time, actually. And when you're actually handling these dangerous fluids, imagine, hydrochloric acid or anything like that, it's great if you could have a robot that could step in, especially as the day goes on and the scientists could become more tired as the day goes on. So thinking about the kind of things we know about the wet lab starting out, a lot of the containers are relatively symmetric. They're easy for people to handle. And generally, the scientists might have a decent idea of the fluids that they could be pouring from if that's what they're doing for the mixology. So here's the general pouring problem. You have a container that you're pouring from, you have a receiver, and our setup, you have some way to observe the volume inside of this container, either using weight or using vision. And as you pour, this is actually a challenging task because there's a time delay that exists for larger containers, which we'll see in a moment. So how can we complete these very complex tasks? So many of you might be familiar with such a diagram for system modeling. So here you have the environment or perception, how you see the world. You have a final task objective, which requires you to take whatever you're trying to do and represent it as a state vector. And you need to start, you have some initial condition, and you need to navigate to your target state. And then you have some control strategies that indicate the actions you need to perform in order to reach that state. But there's a lot of uncertainty at each level of this, right? How do you actually ensure that you're perceiving the environment correctly? How do you correctly model the task? And how do you model the transition between these tasks? And then how do you design that control strategy to execute that? So a toy example here is fun. Everyone loves self-driving cars. So here I'm going to take like the Tesla auto parking example, for instance. So consider this path planning problem. You start at A, you want to navigate to B. You have perception in order to see the cars around you. You have modeling and planning. This is pretty well solved. You have like RRT Connect. You can plan one of these planners and get your path. And then you can control and try and move to this position. However, in the state of the art, still a big challenge is the world is so complex. So how do we extract the state vectors that we care about to do this? So perception in this case is a challenge, but in the future work that I'm going to show you, the work that we're doing now, even the modeling is also a challenge and not well understood. So here's an example of the Tesla autopilot. So here the car is just going back, and then you'll see like the person grab it as soon as it bumps into this car as it's parking into that spot. So while the control Ackerman steering is really well understood, we understand how to do perception, but actually making this more robust is ongoing work. Sometimes it's possible to even learn from your mistakes. So here we saw the car crash, definitely a bad thing to do. However, with reinforcement learning, you can sometimes perform an action, and by making mistakes or suboptimal actions, you can learn from those and then begin to figure out what actions you need to take in order to achieve your goal. So when it's possible to make a mistake, you can actually learn from that in some bodies of work. So here, he trains the arm on what's the correct action necessary in order to open the door. And then he allows multiple arms to work together to actually open this. So success is measured by an IMU that's on the door handle, and they have a recorded sensing that they correlate with success for opening this door. And so by doing this, they can actually learn from their mistakes and learn how to do this particular task. However, a challenge that they face is how do you actually make sure that this learned ability actually translates well to the general problem? So now I want to talk about this in the context of pouring. So imagine you want to pour some acid from container A to container B. This is the initial configuration. You want to navigate to this, right? But you have to pour a specific amount, and you don't have multiple attempts to do this. If you mix these chemicals, you have one shot. So how do you ensure that when you go to do this, you're ready to go, even if you've never observed this container, particular container before? How can you guarantee or give a high likelihood for that success? So to show you how complicated this problem is, I have this cute video. So let's decompose this as scientists. What happened here? So there was definitely a spillage in the beginning. She had trouble perceiving the fluid in the container as she was looking down from above. And then she had trouble attenuating the rotation required. And then there was a significant time delay at the end. She held it still. She was like, it should stop, but it just kept coming, right? So all of these things are also challenging for the robot. And when the robot does it, and if it spills on the robot can't take a bath. We got to buy another $100,000 robot. So how can we avoid the robot from having to learn by mistakes in this manner? So additional task challenges for pouring is container perception. So this is work actually done by Cross's group. How do you actually detect these clear glasses? Then you have fluid perception. So on the one side, you see, it's really hard to see the fluid in there. Can you leverage some tricks with distortion or occlusion to see these fluids? And then how do you actually model these dynamics, which we'll discuss even more in a few slides. So I'm going to present the evolution of the work that we did here. So we started off with what if we actually knew the model for both the pouring container and the receiver? Then what if we only knew the information about the volume in the receiver, but we knew less about the container that we were pouring from? And to that end, what if we could only observe the receiver? And then what if we could observe both the pour and the receiver's essential geometries? So starting off with the first, where we know both container geometries, these are our assumptions that they're both known, no spillage occurs, that the volume in the receiver is observable, and that the time delay between the container falling, the water falling from the top to the bottom is known. And because the geometry is known, we don't have to worry about the time delay inside because we can solve for that mathematically. So the problem statement is, what is the input u, or the angular velocity, required to track that desired volume or height if you know the receiver container's cross-sectional area profile? So related work to this is some work done by Dieter Fox. So his group was actually looking at the volumes in these different containers, and it's similar, but not exactly our problem, in that he was able to classify 11 discrete volumes and use that to detect that, as well as other work that he did where he actually detected fluid in flight using a camera. And then this is work also done where they actually teach the robot how to pour from this exact container, and then they have a target volume that they want to pour into a receiver, but this is demonstrated to the robot many times so that it knows how to pour from this container. And then finally, an industrial solution to having a robot that could actually help pour these volumes is the Monroe lab assistant. So this one uses pipettes, but if you actually look, it's a very cluttered environment, and this can't really work alongside a human, and it's not very versatile. If you wanted to do other things like carry and everything like that, it's really focused on doing just this one task. Okay. So our fluid detection methods, we have a platform that we developed that allowed us to, number one, get the mass of the fluid inside of the container with this scale, and then secondly, we were able to track the volume inside of the receiver using computer vision. So we used a neural net that was actually able to take that information in, half of a convolutional neural network, and extract the water pixels. So we were able to combine these in a common filter and extract the mass of and the volume of the fluid inside of the receiving container. So in this work, we had this MV BlueFox camera, we had the Rethink Sawyer, and this container, if you want to look at it, is actually a square container. And this was because it was easy to model the flow from this container. So this is the original problem. So if you actually have a time delay in this system, but you can account for that, then you have the height above the container, that is how the fluid actually leaves this container. You have the fluid below the surface of the lip, and then this is pouring into the receiver. And these volumes are captured in these two equations, where this is the cross-section of the receiver, and then this is the volume above the lip, and this is the volume below the lip. So doing this, we can actually model the flow rate of the container simply by differentiating our original flow rate model in terms of these parameters, right? Again, you have the cross-sectional areas, and then the derivative of this volume with respect to the angle as you rotate it as it enters the receiver. And then if you want to model how the fluid exits at the top of the container, you can actually use Bernoulli's equation if you make assumptions that the fluid is incompressible and is able to flow in this manner, and you know the viscosity. So with a known container geometry, here we specify the container parameters. You have the length parameter on the container, you have the height above the pouring lip, and then you have the main height of the container, its width and length on the side of the container. So with this information, we can then begin to differentiate this model and estimate what that volume flow rate would be. So if we differentiate that flow rate model from the previous equation, we have this single line here. And so if we expand this and substitute our terms, which you saw for the container geometry, we have this as our complete dynamical model when we know everything about the container. So if we define our state space here as the height, the derivative of the height, and the angle of the pouring container, then we can write the equation we just saw in terms of this dynamical equation here, x dot equals f of x, g of x u. It has that really nice form. And we care about the two outputs of the height inside of the receiving container. So if we define our error in terms of this output, so the height and its velocity, we can specify a trajectory that is a fifth order polynomial, so it's very smooth as we pour to minimize sloshing inside of the receiver. And if we have the model in this form, we can show you that it's actually linearizable, feedback linearizable, because this matrix is full rank and involutive. Right? And so this is the case when your velocity is not zero in the receiver and you're not tilted beyond 90 degrees in your container. So with these conditions, we can show that our objective function is to minimize the error between the trajectory we're trying to pour, given the dynamics of the system. And we propose this hybrid controller, which takes into account all of the dynamics when pour is initiated. It initiates pour to get into that state, and if it's outside of the region it can pour, it simply stops. And then we can show that with feedback linearization, this matrix becomes stable with these conditions on the gains. So the output of this is our ability to actually pour precisely different target volumes. And then here's showing some statistics over 100 pours for that square container. We're pouring at a target 100 milliliters. And then this was initially, in our first attempt, the error between the scale and the actual mass that was being measured. So here's a quick video showing this work. So here you can actually see the robot begin to pour. I can speed this up. And so here initially we had to have the fluid as blue because we used online subtraction. But then in our later work you'll see that we applied that neural net to detect the fluid, and you can see that it's actually able to detect clear fluids of any transparency when you leverage the distortion of that background. So here we're actually able to pour very aggressively and quickly. The red line is the target line that we're trying to reach, and then the green line filters the fluid above that, and we're actually able to detect what we believe is fluid entering versus fluid of the rising, and use that to detect the mass or volume inside of the container. All right, so this is the case when we know both the pour geometry and the receiver geometry, but what if one of these is unknown? What can we do in that case? So we're going to move now to the case where we can only observe the receiver volume. So here we adjust our assumptions that only the geometry of the receiver is known, no spilling occurs, and the volume in the receiver is observable. So then, given these essential characteristics, then can we actually track the U that gives us the height that we want inside of the receiver? So here the time delay is important, but in this stage of the work, we actually assumed that it was constant, so about a second. And then we actually showed that the results weren't great because in reality, if you saw, remember when she poured the milk, that actually can vary depending on the angle you're holding it. And so later we learn exactly what that is. So taking the derivative of both of these volumes, here we can actually restate our volume equation. So again, this is similar as the dynamics you saw on the previous slide. And then we have, again, we're looking at the height inside the receiver. We can actually say, if we have this time delay, we can actually say that the future time delay can be observed by integrating all the actions we've done until this current point. So this is our previous height. These are all of our actions up until a current time. What do we expect to occur based on everything that we've poured and acted up to this time, given our knowledge of the container? And so we need to estimate, in order to do this prediction, we need to estimate this derivative profile of the maximum volume profile. So what is this maximum volume profile? So given a container, if I have the maximum volume it can have at this particular angle, it should describe some curve in this manner. So what's the max height versus the angle? So you can pour many containers and see in the receiver what this profile would be. So this is pouring these very slowly and watching how the height changed in the receiver from these different containers as they were poured. You can do the same thing in simulation, which we'll talk about more. We used NVIDIA Flex to pour these profiles, and you can actually generate this simulated data if you can model the fluid correctly. So what we want to do is actually approximate this volume profile. In this work, we said, okay, we're only observing the receiver, so we need to actually be able to leverage information about all the example pours that we've done. So what if we model this with an orthogonal basis? So we used a Legendre basis, but you could use any orthogonal basis. And what was great about this was it allowed us to use the coefficients to represent the containers as a point in space, right? And so then containers that are similar geometry should actually cluster together, and then we can actually use that information if we normalize them to predict how we expect our current container to pour simply by watching how it behaves in the receiver. So here's the objective function that we try to minimize. As we begin to pour the fluid, we're trying to approximate that volume curve. This is done with this residual. We have this weighting function which says, okay, initially, if I'm actually just starting to pour, I need to really trust the examples that I have, right, which were those practice pours. But as I pour more, I can begin to trust more the system identification as I continue to pour. So here we have a similar state space. Our dynamics are slightly simpler. Here we have, again, the area of the receiver. This is the dV d theta. And then we have our output, which is just the height inside of the receiver. And we want to actually track this error at some future time. And we show that the system is input-output feedback linearizable if these conditions are true. And they're pretty straightforward. So then here is our objective function. We want to track that error as well as optimize and figure out the container geometry at the same time, subject to the system dynamics. Again, we propose a hybrid controller very similar to the last one, initiate pour, and then account for the dynamics when those conditions are true, when pour is initiated. And again, this system is feedback linearizable, and we can show that it's asymptotically stable. So here's some of the data for this case. So here, pouring this container, you can see the measured, modeled, and actual trajectories that you're trying to track, the predicted height at that time delay looking a second forward, and then the commanded and actual angular velocities, as well as the profile dV d theta at a given time that it was sampled in your state space. So this is optimizing as you continue to pour. And then we show repeatability over many trials. How does this perform? And then if you look at many different containers, you can actually see that if you compare our method to pouring very slowly, pouring with medium speed, using just a KP feedback, and then our method does a really good job of trying to stay lowest in this curve, coming closer to this low volume, low time compared to the stratification of all the other methods. And that's usually between 30 to 40 seconds, and a final error from 5 to 20 milliliters. So there's still a decent spread, and so our latest method actually improves on this metric. So this video quickly shows the simulated pours that we use to train this system. So here, the robotic manipulator is going to practice by pouring these row containers, but then we can actually use the simulated data. Here, these containers have particles, and these particle interactions in NVIDIA Flex are used to simulate that of water. So in this work and in our later work, we actually made sure that this actually matched real pours that we poured to make sure we tuned the parameters to represent fluids correctly. And so using this information, we could then pour from a set of unknown containers and reach this target volume of 100 milliliters on each one in relatively low time. So this is sped up 3 times their actual speed to show that we're able to reach these target volumes. So, okay, so we've been able to show that if you can actually see the volume in the receiver, right, then you can actually approximate that information and pour precisely. But there were some tricks in there, and the main trick was, as we were doing this optimization, we were trusting these models initially, but then as we begin to continue to pour, we began to trust system identification more. And so there were a lot of terms inside of that optimizer that we actually would have to tune to make this more adaptable to any system, and that's disadvantageous. So how can we actually improve this? And this is what our latest work has been on. So now we'll focus on what if you can look at the pour as well as the receiver, what can you say in that case? So here, the key adjustment in our assumptions is that the geometry of the pouring container is now observable. Now what can you do? And then you have a similar problem statement. You want to find the input velocity to reach that target volume. So here's our full system state machine now as it matured. And we'll have a video showing this done in the KUKA Innovation Award. But the highlighted parts here are the scanner geometry and performing the precision pouring. So here's our complete setup. First, the system scans the container, and then it pours it inside of our objective. So now this is the simplest form of this dynamical equation. Here you have the time delay in the receiver after some time TD. You need to know what that is. This is the velocity in the pour, and this we're going to use this notation to represent that volume profile, V sub theta, and this is its first derivative with respect to theta, and then this is our angular input. Right? So now if we want to think about what the time delay is, right, we can actually think that it's a function of the container geometry, the angle at which we're pouring, as well as the angular rate at which we're rotating. And our objective is still to track some desired height in the receiver that we specify. So for actually extracting that container geometry, we have the sensor set up here. We have a time-of-flight sensor, the PicoFlex. It's actually able, if you have the right color for your container, so here we had to use white paper, you can get a really nice point cloud. If it has the wrong material, sometimes it's actually spotty, so we can continue to improve that. But then with this, we're actually able to extract the point cloud and reconstruct the geometry of the container by estimating a set of of cylinders at different heights. After getting ransacked for the table, you get the table normal, and then you subdivide that and group these pixels together, points together, and you can actually construct these cylinders and then fit a Gaussian process to this. So what's really important to note is that when we fit these curves, which is useful for comparing, we always fit them with the same number of points, 128 points. And that was useful, and they're spread out over the height of the container. This is useful for actually comparing against simulated containers, which we can also get and extract that profile for. So here we're actually pouring this some fluid inside of NVIDIA Flex. So we have the same particles, but then you can render this with the fluid. And then if we have thousands of these containers, we poured 3,288 of these containers, then what we actually can say is, what are the top 10 containers that are closest in the geometry from the container that we're pouring from? So after we extract our profile, what are the closest ones, and what is the percentage that they are? So then once we have the profiles from these simulated containers, we can then use a mixture probability to estimate what we believe our container would behave if our container was actually close to these simulated containers. So here's our control diagram. So here we have the model which we're trying to estimate. What is that volume profile? What is that time delay? And if we can estimate those, we can control our input to reach that target volume, where here error is defined as the desired and actual difference in volume. So we want to effectively combine online system identification, which we did in the previous work, along with sufficient model priors that we can use from the beginning to actually help us pour quickly and precisely. So for system identification, now, because we're actually going to do this in a different space, we transition to power series. It's not necessary that the coefficients be orthogonal. And we want fitting for the system identification that minimizes this objective function. So again, minimize that residual as we pour. We want to have a regulator so that our curve doesn't diverge. And then we want to have soft constraints because the physics say as you pour it into the receiver, the volume should never go down, it should only go up. So have this constraint on the derivative to make sure it's strictly positive. So then for the Gaussian process side, if we want to compare these different methods, we don't have to use just the online system identification. What's the model prior aspect here? We use a Gaussian process. So here's the kernel that we use. It's a combination of a radial basis function with white noise. And the variance here is a function of how well our container fit to the container that we're comparing it to. So given this information, we can define these covariance matrices, which are a function of the angles for both of these, the training and the test container. You can then construct the information matrix, and this is textbook, and then you can actually have this non-parametric estimate where we combine each one of the fitted volume profiles using this mixture probability that we obtained. And this is in addition to accounting for how close we are to the container. So if we're really far from the container, this variable becomes very large, right? And then this kernel gets very large and there's disassociation. And so you'll converge to your mean in that case. And if you're very close, this will become very small and you'll be very tight to your mean. And this gives our new algorithm the ability to be very adaptive. So this is the combined system. Here, this is our final our volume profile. This is the parametric side, which we talked about, the power series. This is the non-parametric, the GP. But what we've done to combine them is we've actually made the parametric the mean of our GP. So if our containers don't fit very well to the container that we're testing it with, then our variance allows that to loosen up and will converge to the mean, which is our online system identification. But if we're doing a really good job and we have enough data points, then we can actually leverage information about our model priors. And in this way, we have a system that's able to adapt with few examples. Can we actually correlate to an example that we've seen? And if we're far from that, can we actually account for that as we pour and still perform very well? And so all of that is in one equation, giving this hybrid structure so that it can perform well in either of these scenarios, which makes it robust if it's far from that training set. And this is something you don't see too often in related work. So how do we approximate the time delay? So again, we had these mixture probabilities. We assert that the space is continuous, right? And this is our structure for our neural net. So we input our geometry into a convolutional neural network with 3 of them in a row, and then we combine this with our angle and angular velocity in a fully connected 5-layer, and we were able to extract our time delay. And so our hybrid control strategy in this case is a little bit more complex. We have some hybrid guards and resets. Again, this is the state of the pour. This is the derivative of that volume profile, the volume rate in the receiver, and then the error from our tracking volume. and we have a similar one you can notice as previously. So this again initiates the pour, right, and then this accounts for the pouring that specific amount of volume that we want inside the receiver. So why should this work? So controller stability, if we actually look at the error that we expect to see at a future time, you're pouring that milk, you stop, right? All of that action basically will influence the time you're at plus TD, right? You want to minimize that error at a future time. So how do you control with a time delay in your plant, right? So here this actual can be written in this way. So integrating from the beginning of your pour till now, all the actions that you've done, this is what you want to mitigate, right? And so we consider this Lyapunov function, right, which is just the square root of this error at that future time. And then the conditions for stability is if you're not telling the desired volume to change, right, then it's stable with this condition, where here your Kp has to be positive and your angle, maximum volume angle has to be positive. And those are given if you're respecting the physics. And then if the tracking velocity that you're trying to pour is non-constant, then this is your scenario, where essentially this says you have to have a large enough error in order to begin to track that desired volume. And so it's kind of like an escape velocity. But if you make your Kp larger, then the error that's required to make you track that asymptotically becomes less. So here's how we actually generate our trajectory. So here we use a trapezoidal trajectory generation, and here's where we get our optimal time. So we take our maximum velocities allowable, accelerations, and then we have these minimum maximum velocity and an upper maximum velocity. And this is determined by how well your volume is fitting. So if your container is doing a really poor job, then you should minimize how fast he's able to pour, or she is able to pour. And then if you're doing a really good job, then you should actually speed that up, right? And then the volume under this is the final volume that's your target volume. So showing some of the results here, this is for this container. Each one of these represents 30 trials each. And then you have the associated time for each one of these methods. What you begin to see here is for 100 milliliter pours, right, the parametric method where you're just fitting that power series does a decent job, as well as the GP. If you actually look at the volumes here, they're not bad. This is error on the final volume. So this is about 3 milliliters. So compared to what a human can do, this is comparable. And then if you look at 150 milliliters, you can see that the parametric method is slowly beginning, to increase, but the GP is relatively staying consistent even as you pour to 200 milliliters, right? And so this is the relationship between that volume you pour and the respective error at the end of the pour. So comparing across different containers, again, each one of these represents the trial, right? We can then associate different geometry relations to different one of these containers, and then compare the performance of each one of these metrics. And what the real takeaway here is the fact that regardless of how the parametric and the non-parametric perform, and usually one of them does really good, the semi-parametric usually interpolates that for the major statistical portion of that. So if you combine these methods, this justifies the fact that you can actually do the best of both worlds as opposed to having just one across multiple scenarios. And this case shows what happens if you do a really poor job of actually fitting this container. So these are from the previous slide, but here we said, okay, what if your container is very far from the training set? How can I expect to perform? So here the GP is horrible, about 10 milliliters or more in these pours, but the semi-parametric, which combines them, still does comparably well to the parametric. And you can see that switches depending on who's doing better. So semi-parametric really does a good job for that. And so here's showing the actual volume V theta curve. So this is theta, this is volume, right? This is using the semi-parametric method with this correlation between the containers. And here, because this was actually very close to a lot of the training container sets, the semi-parametric didn't actually have to travel that far, which is the times that you see here. And so this curve did a really decent job of fitting that. This is the same curve. The orange dots represent the red ones here. And then these are the training container profiles that you were able to see. So here you can actually see for 13 different containers, combining the 3 that we just had, what was their final error for 10 pours versus their height. And so you see that there's this general uptick, and we associate that with the fact that across all of these containers, the velocity, maximum velocity, lower bound we kept constant. And so if you actually allow this to be a variable with the height of the container, you can actually make this plateau even more and have even better performance across the board. And so here's an association, sorry if you can't see these statistical boundaries here, but for these 13 containers, associating the air along with the final time that it took, and you can see that we were usually between 20 to 40 seconds, and we actually did below 5 milliliters, and this is comparable to what a human would be able to do. So here's our work shown, the system at the KUKA Innovation Award. We scan the geometries, and we begin to pick it up and then pour it. In the interest of time, I'll show you the main video, which you might have seen before. So here, they did an amazing job with the video. You have an interface, you select how much you want to pour, it scans the area, picks up the container of interest, transports it to the region where you want to actually do the pour. You can see our system set up here, and in a moment you'll be able to see the output. So it begins to pour, it's initiating that pour. Once it figures out what it's doing, it begins to speed up. And so it actually looks like a person would. It will start to pour, and then it like backs off, and then figures it out. But then every single time, we're able to pour precisely using this system identification. And then we just simply motivate why this is good for a scientist. I've been told that I look like someone off of Westworld, but we'll ignore that. So, okay, transitioning quickly to carrying. So this is another useful task that we could have the robot do. Again, we consider this scenario. You have, you need to measure your environment, observe the human. You need to model the human, model the combined systems motion, and then figure out what the robot inputs should be in order to execute that motion. So here is an example video showing where these movers are moving a piano, and they're actually, if you can hear, they're doing this quietly. They're figuring out how to navigate around obstacles in the room. The piano makes some noise, but they're quiet. All right? And so this is an extremely heavy thing, but everyone knows what to do. So if we wanted a robot to help a human carry something like this, how could we actually give the robot the ability to know what to do in that similar fashion? So our first step was to actually look at how ants would do something similar. So here you see all of these ants, they're carrying this thing, they're able to avoid obstacles, so the ones closer to the obstacle are like, hey, back it up, and then they're able to push it and navigate without striking that obstacle as they navigate toward the nest. So like, ants can do it, we can do it, so robots should be able to do this. So here we generated a sensor. This one we put pomegranate juice on the end so that they think it's food. A lot of wasted energy on their part, but we were very happy. We have these fiducials on top, which allow us to actually track the forces that they're applying. So here is a top-down view. So if you calibrate this sensor, you can then track the deflection, and that tells you about the forces that they're applying. So what's really nice is, related to work that Spring Berman did, she said, over this short interval of time, 20 seconds, we kind of saw the interaction forces decrease. So for us, if you actually look at this entire trajectory, and this is where the majority of the data was collected over 23 trials, for 200 seconds, we saw the same thing. So this interaction forces, or the stresses that they're producing on this object, they needed to minimize, and if they could do this, this kind of defined what optimal transport is. So we define optimal transport as going from pose A to pose B while avoiding obstacles and conserving energy. So the first step of this is, okay, let's say I knew where I wanted to go. How do I actually plan on where's the most logical path to get there? So this is a good problem, and we did work here that actually augmented this by actually having a system. If I can fast forward to the part here. that allowed us to construct safe corridors that the robot could traverse through that really lent itself to the path that the robots were trying to follow. So here you see each one of these nodes generated from a seed path generator. You can imagine like a sample-based planner, and then you construct these overlapping convex corridors, and you can plan nice, smooth, optimal trajectories in that space using those corridors. So if you know where you want to go and you know your complete environment, you can plan a safe trajectory to get there that doesn't have any collisions as you do that. So given these interaction forces, we want to minimize these two in order to be optimal. So work that was done by Vijay and Waldron back in the day was actually saying that if you actually have this wrench, you can actually look at the interaction forces, and if you make them all reach consensus on what this coefficient is in order to describe their force, then their interaction forces will be 0. And we wrote a paper that said if your robots can talk to each other, they can reach consensus on this vector and allow them to actually not have any interaction forces, which is really good. And so toward this end, there's a lot of related work on having these robots that actually carry using compliant transport. But in all of these examples, there has to be some force that's being applied in order to make the robots move, right? But if they want to be intelligent and actually approach that optimal transport, if they could guess where the human wants to go, then the stress can go down as they're navigating in addition to being compliant. So these are the assumptions that the human knows where they want to go. They don't want to collide with any obstacles. The human wants to conserve energy, which implies minimize that stress on the system. So how can the robot observe the human optimally transport when explicit communication is not available? So technical challenges to this are human inputs and the load dynamics need to be modeled. The robot needs to support the majority of the load, and then you need to actually find the most likely path that the human intends to follow. And so toward this end, we began to think what kind of things would be useful for the robot to actually extrapolate these necessary quantities. So one we thought of was we could look at the direction that the head was pointing. We could look at the way the step vector was pointing as the person walks. We can then look at the surrounding obstacles. So here, if you can imagine transforming this to this map, you can treat your image map as an input for constraints from where you could go. And then each one of these things could actually influence the second derivative of where you believe the system will go, and you can integrate that to extrapolate where you think the human intends to go if you integrate twice for the acceleration. And so here you can imagine the step or the head describing how you'll actually accelerate based on where you're looking. So you're going to go in that particular direction. So we began to do this. We said, okay, it's actually extremely difficult to model, as you can see on the previous slide. What parameters do you choose? What form should you choose? How do you know it's correct? Do you need to have multiple models to do this? So one thing we thought was, well, how about we just try to see if we can learn from how humans do this? So if you have all of these inputs and you can extrapolate a map, we have a sensor that allowed us to extrapolate the wrench, the head vector, the step vector, and then see how two humans would carry this. And we did this on a range of maps. So here's the wrench being applied, the force, the moment, and you can barely see it, but there are reference frames which show the direction which our head was pointing, and then the blue is our feet as we begin to walk. And so using this information and watching where that map is, we can use this to actually build a model, a representation of how you can expect those inputs to inform where you're going to want to go on some time horizon. So using this information, if I have this robot and this robot has a holonomic constraint, then you can imagine that this can become challenging. So how do you decouple this and make the system capable of doing this? So for the arm, we propose to use compliance. So here, these are the joints and the torques that you apply. And then using this principle of virtual work, you can say, okay, this is the stiffness if I want in the end effector, this is the stiffness that I should have in my joints. And then this is the dynamical equation that you have for the torques. So this is the inertia, you have your control objective, Coriolis, and gravity terms. And then how do you control the base? So if your arm is simply compliant as it works with the human, then your base can do all of the necessary things to drive the motion of the robot to help your system go where it needs to go. So to do this, we propose some base kinematics here. You have just the non-holonomic base. And then you can have the active compliance. You have your dampener. and your joint repulsive system to make sure that you stay away from hitting the edge of your arm. So quickly describing what this looks like, you have this human, you have the table, you have the robot, right? And then you have this constraint that your arm always has to be holding the table. So this is not like a usual differential drive robot. So if you have an objective, how can you actually navigate the system to that, accounting for the non-holonomicness of your base, and at the same time avoid any jackknifing that might occur as you try to attenuate that. So we proposed a hybrid controller that accounted for these, and if you're interested, come speak to me later, and I'll be happy to lay that out. And then you have your feed forward objective, which predicts where the human wants to go, and your feedback with compliance. So just showing how we're actually able to detect these different things. Here is some open source code that just uses the laser to track where your feet are, and then we place this entire system on the fetch. So this is an earlier implementation. My code runs a lot faster now. In a minute, you'll see the head post snap to the right position when it finds my face. And then this was the wrench being applied, and then the step vector, as you saw in the previous video. So in conclusion, Precision Pouring Wet Lab Assistant is awesome because you can actually have a robot that's capable of pouring from common containers found in a wet lab. It's capable of pouring precisely given a target volume and requires very little augmentation of the environment. And then you can have a cooperative carrying assistant, which we're continuing to move toward, where we define optimal transport as being synonymous with minimized stresses on the object. And the proposed system is capable of not only compliant transport in the presence of interaction forces, but predicting what the human intends to go with this model. So finally, I'd like to acknowledge both of my dissertation advisors for all of their help and guidance, committee members, the GEM and NSF Fellowship, and all my wonderful collaborators, which if I did not have them, I would not be at this point today. So thank you all. Thank you.
Thank you very much, Monroe. It's a challenge to present a lot of material.
I noticed the little girl in the movie was having trouble with the mass of the fluid as well, too. I'm wondering, I'm guessing that as the volume increases, the mass effects, which you've ignored successfully so far, are going to become, if not overwhelming, then still pretty challenging. You have some sense of, how much more volume you could have handled for the mass effects being, or then what you might do with that from there?
Yeah, so that's a great question. So whenever we poured with the Sawyer, we actually had far less volume containers, if you notice in the video, than we did with the KUKA. So usually our threshold is if the robot starts making any noise that sounds like anything like it's in trouble, we back off and do it in that region. But if you have a robot that's actually able to handle that, those dynamics can still be important, like imagining for the KUKA and torque control. That's going to be different just because the inertial properties of that fluid are actually different. So if you know the density of the fluid that you're pouring and you can somehow add an additional segment which can estimate the volume in the container when you pick it up, right, then this becomes a very interesting conversation because it's not a rigid body dynamics as you pour it, and the volume is actually shifting as you begin to pour. So I think this would be a really interesting aspect to model as well. And then this also correlates to the aspect of not spilling. If you're very aggressive with this, you know, this could go everywhere. So how do you actually model the dynamical fluid is, I think, a really interesting extension, and you can model that as well.
Just to poke you a little bit on that, my guess is that if you begin to think about the changing mass due to the large volume, that the optimal control formulation may not be your friend anymore. That the ability to tune up the reference trajectories in the space of cost functions may be very, very hard.
Definitely, possibly. Something else too is just from playing with things, the intuition would also be to actually try and see if you could leverage compliance. So imagining I had the control authority to handle any of that, right? Could I actually leverage compliance to serve as a dampener of the fluid and kind of do a robust control side too? But ultimately, you can imagine a scenario where even if you have that control authority, if you have too much fluid, this is simply going to be a problem. And then this comes back to how do you just model this appropriately? And I think that's an interesting line of research.
So did you look at all at how accurate humans are for with these containers? Whenever I've been in wet labs, that's not the kind of containers before with much longer, thinner things.
Yes, right. So that's a really good point. So for the container we're pouring into, right, we had like a stout 100 milliliter container. So for non-aggressive, pours as an initial, initiation of this robot into the lab, I would say it's comparable to what a human could do pouring into such a beaker with the precision that a human could do. But you're absolutely right. The very long and tall beakers are extremely hard because you almost see nothing in the beginning, and then you reach this like critical zone where just a few angles are extremely sensitive. The girl would have a horrible time with such containers. And so one thing you could think about is, like we were mentioning, minimizing that the maximum velocity you have to pour from given the height of the container. If that's a function, then you could possibly slow down and handle those containers. But as a first attempt and a proof of concept in getting this to work, we didn't do those long ones. But they're sitting there staring at us, telling us they're waiting for us. I can't say in front of the crowd, no. So fortunately, we only got stuff on the gripper, and we have these little BBs that we pour first when we're testing on new robots. So like we were doing that from the KUKA, and when we went to Germany, we were still getting everything to work last minute. So we actually just put sugar in the container just to see, and we did spill sugar. So being a manipulator guy, like the KUKA is like 100K, the fetch is 100K, you don't want to spill on them. So like having benchmarking along the way is extremely important. So now we're actually planning to do something with the fetch. I actually put like a rubber glove on it because if you look in the middle, you can see right into the gripper where the worm gear and motor is. So if something dripped down there and it's holding it up, it'll just burn it out in one shot. So, you can imagine it's really important to take those precautions. So I have made spills. Most of them, they just spill on the table, and we're usually quick enough to be like, something happened. And we do our math, so it doesn't happen too often.
You said this was funded by GlaxoSmithKline. So, like, are they going to actually use this, or like, is there a procedure testing this for it to be ready enough?
So that's a great question. So we did this through like NSF's IUCRC, so they combine universities with companies, so we had like a relationship with them through that. So they brought this idea to us and told us this was something they wanted. The caveat to that is they were like, we want to pour this, but we also want you to like mix some powders in as well and add that in. And we were like, okay, liquids seem doable in 2 years. Powders are going to be a little more interesting if you want to be extremely accurate with that. So I think that this will be useful soon. They have these sort of platforms on their site, like